packages like GNUplot, pgplot, SM, etc. They are all available as modules in Python. They're all available as modules in Python. Shall I start from the beginning maybe? Record hota tha? It's on. Okay. Okay. So these are all available as modules in Python for you to use. So if you are already a master of plotting in one of these packages, it may be more efficient for you to use them. However, if you are not and you want to stick exclusively to Python, Matplotlib, which is the standard plotting library for the Python language now, provides you with very large number of plotting capabilities. Okay. So before we actually started looking at some plots, I would just like to show you this website which I mentioned on that page, which is called the Matplotlib thumbnail gallery. Okay, and here you have gallery and you have sort of examples in so many different categories: how to make subplots, how to show images, how to use color, how to use different shapes and collections and so on. And then what they have done is they have given many examples for each of these categories. And not only do they give you the example, if you click on any of these, what you get is the output, but you also get the full program that produced that output. Okay, so just like we are giving you notebooks for you to practice on, there are literally, I think, more than 1,000 of plots. We'll just scroll through a little bit to just give you a feel for what is the diversity of plots that can be produced using Matplotlib. In fact, almost any kind of plot you can imagine has been covered. And in the limited time available today, I will not be able to cover too many of these categories. But this is just to show you that yes, it's possible to do many different kinds of plots in Matplotlib. Okay. This goes on and on. Matplotlib incidentally was developed by people who do MRI imaging. So if you ever get an MRI scan done, then there is a high probability that the plotting software that they use will be using Matplotlib. Okay. So yeah. So that's it. So literally, as I said, about 1,000 examples are there for you. But now we'll take a sort of bird's eye overview and look at some most commonly encountered or most commonly used kinds of plots. Okay, so first remark is that the Matplotlib commands or functions are by design identical to those used in MATLAB. So if any one of you has used MATLAB, okay, you don't have to learn anything new. Exactly the same MATLAB commands will work in Matplotlib. Okay, in fact, the Matplotlib is the name itself is derived from MATLAB. For basic plotting, it's easiest to use a sort of alias to this Matplotlib module, which is called pylab. Okay. You can start it from the command line by issuing the command ipython ---- pylab. Okay. Or if you already have a ipython session open, you can give the command %pylab or %pylab inline. The only difference between these two is that in one case the plot will be produced within the browser, okay, inline in the browser window itself. In the that's when you do pylab inline. If you do only pylab, then a separate plotting window will open in which the plot will be generated. So for the purpose of this talk, I am going to use pylab inline throughout. But I must caution straight away that in a real program, you should never have this. Although in principle you can do it, in real programs, you should never, what this actually does is that it imports the entire Pylab and NumPy namespaces into the global namespace. So Pylab, it imports the entire Matplotlib namespace into the global namespace and overwrites any things that you have defined previously, okay, or any built-ins as well. So it's a very, very dangerous thing to do in a non-interactive program. But if you quickly want to check some data out, you want to make some plots, and you are not really doing it as your final paper version, then it's okay to use this. Because, so in today's talk, we'll be focused on interactive plotting. But any kind of non-interactive plot that you do must use the full syntax. So don't do percentage Pylab inline. What you should do is you should do import Pylab and then do Pylab dot some command, Pylab dot some other command, so on. Okay? Don't, this is like really a very, very strong warning. Okay. So I did percentage Pylab inline. And it says populating the interactive namespace from NumPy and Matplotlib. That's what it does. It imports lots of functions. You don't have to. So it does from Pylab import. Okay, which is exactly what we told you never to do. Okay. So it even warns me that there was some variable that I had defined which was called f. Okay, and that got clobbered. Okay, which means it got overwritten by some other variable f coming from Pylab. So that's okay. For now, we are going to ignore it. Then what do you do? So let's begin to try and make our first plot. We'll do that by just making some x and y data. What it has done is it's imported NumPy as NP already. So we don't have to do that separately. X is equal to np.arange 0 to 6.28.01. I want a list of all numbers between 0 and 6.28 in steps of, okay. Remember, in A range, the last thing is excluded, so it has to be less than 6.28. So 6.27 will get picked up. That will be the last number in this array, a one-dimensional array of numbers. Then I do y is equal to np.sin x. So I basically take the sine of all the x values. Now we plot y versus x. Okay, and the plot command is ridiculously simple. You just say plot x comma y. You tell it what variable goes on the x-axis, what variable goes on the y-axis, and it will plot it. By default, it not only plots the points, but also connects them together with a blue line. Okay, so in this, actually it doesn't actually show you the points it has plotted. It actually by default only shows you the line connecting. Okay, and since these were all in order, it plotted a very nice sine curve for you from 0 to 2 pi. Okay, so that's your simplest plot. It's very easy to do. So we will start playing around with this plot and try changing colors, try changing the labels, etc. etc. Okay, so first thing we want to do is we want to add labels. So what we do again, plot xy, and we say now what it does is there is a Matplotlib which is called pyplot. Okay, so it also does, among the various imports that it has done, it also does from matplotlib.pyplot import matplotlib as plt. That's the standard short form for that. So that's already done for you. So if you say plt.x label theta angle in radians, give it a string, it will put a x label there. Similarly, a y label will appear once you put plt.y label, and if you want to put a title, you put a title, plt.title. Okay, and give it a string. Yes, so that's the next step. So people will say, no, with this theta we want a Greek symbol there. How do we use Greek symbols? Okay. So if you want to use Greek symbols, and you'll see here that there are Greek symbols, you do plot xy, but instead of saying theta as a string, what you do is you put a r in in before the quotes. Okay, the R tells Python that whatever follows should be interpreted as what is called a raw string. Okay, so what is follows is a raw string, so it should be processed before it is rendered. Right? In order to do that, it realizes then that these $ signs indicate that there is some mathematical symbol inside. Standard LaTeX like symbols work. Okay, so raised to something, everything is exactly the same as LaTeX. So the dollar indicates that \theta should be interpreted in a mathematical sense. So it realizes that, it puts the theta symbol over there, and the rest of the string it doesn't have to interpret anything, it just prints it out. Okay, similarly one for the y label also one has put r sine theta, and this of course is a nicer plot. Notice that one is actually xlab, ylab the title. We could have just given the commands, but instead of that we have put a variable name in front. Okay, something is equal to the label. Okay, now what do you think this is? Like, what is xlab? Is it an integer? Is it a float? What is it? Is it a string? No, it's not a string. Is the X label object. Okay, remember in Python everything is an object. Okay, even a variable is a kind of an object. A file is an object. Okay, even the label of a plot, the plot itself is an object, and even its label, X label, Y label, and title are separate objects. Yeah. So what we have done here is, once we set these as objects, we can do things like the title dot set font weight bold. So now set font weight is a method associated with the title object. Okay, which in our case is the title. So we have made the title bold after the fact. Okay, so this would have just rendered the title. This makes it bold. Similarly, ylab.setColor blue renders this text blue. xlab.setColor red renders this text red. xlab.setStyle italic makes the X label into italics. Okay, so you can now, since all of these are objects which have their own attributes and methods, one can manipulate those attributes any which way one wants. Okay. If you want more examples of how to basically modify the basic features of the plot, like changing the fonts, colors, background, weight, italics, bold, etc., go look at this particular URL. What are the other things you can set? So before we look at that, we are going to make something called anotherx equal to x plus 1. What was x? It was all numbers from 0 to 0.28, 6.28 in steps of 0.01. So 0, 0.01, 0.02, etc. Another x is equal to x plus 1. So it's another sequence of numbers now, but instead of starting with 0, these numbers are going to start with 1, and instead of ending at 6.27, they will end at 7.27. Okay, that's all. Now we say plot another x, comma, another x raised to 4. So we are basically plotting x raised to 4, where x goes from 1 to 7.27. Okay, and we give it a title, x raised to 4 versus x. Okay, and this is the plot that it makes. Now notice here that we have everything to its default value. Okay, and for Matplotlib, the default is that the curve, or the first curve that you show on the plot, will be blue in color, the box will be black in color, okay, and the tick marks and the tick values will also be black in color, okay, and title, if you give it, it will also be black in color. These are the sort of the default color scheme. Of course, you can change it any which way you want, and we'll keep on changing it. Okay. Now we want to make it look a little bit better. Okay. So what we do is, we again plot that same thing. We give it a title, but now we have changed it again into a raw string, because write x raised to 4, okay, versus x. Okay. Then we change the x limit to go from 1 to from the minimum value of another x to the maximum value. X will be 1, maximum value will be 7.27. Okay. And for some reason we decided that maybe it was nicer to show it the y scale as a log scale. Okay, so this becomes like a semi-log. Y-axis is on a logarithmic scale, and the x-axis is on a normal scale. Okay, and plt.show, this command is redundant. It will already show it because we have done pi. Okay, but if you are doing it non-interactively, you may have to give a command like show. Okay. It's also possible very easily to overplot one plot on top of another. Okay, so in the first command we plot our x and y. Basically, we plot sin x. In the second plot, we plot cos x. Okay. Now by default, I said that the first plot that you make will be in blue color. Okay, and since we didn't specify any colors, the sin x curve came out in blue, but the cos x has come out in gray. Okay, so by default it sort of cycles through various colors. Now if I make another plot, okay, y equal to x, for example, okay, it will make that in some third color, and if I put one more plot, it will make it fourth. Remember that the dimensions of this box, since I didn't specify them, are divided the first curve that you plot. So if the second curve that you plot spans a sort of wider range, only a small section of that corresponding to this rectangle will show in your curve. The rest of it will not. Okay. What does this indicate? Can someone tell me? Matplotlib.lines.lines2d, line 2d. You would have seen some mysterious things like that elsewhere also. See? It's actually just the object corresponding to the last command that you gave. Okay. Since here the last command generated lines. For example, this would have generated this particular line, right? The last command. That corresponds to the line object that you have plotted below. Of course, it only shows you the object, last object plotted. So for example, if you went back, here it shows you that this is a text object. Okay, although there is a full plot underneath, because that text object corresponds to plt.title, which is a title text object. Okay, so this is just to emphasize that everything here is an object, and we are creating objects and then manipulating them. Okay, let's go on. You can change styles, symbols, colors. Here is one example of that. Okay. So what we do now is we create another array, xspaced, which is again goes from 0 to 2 pi as before. Okay. Here I am explicitly using np.pi, which is the value of pi. stored in numpy. But I am going to do it instead of in steps of 0.01, I am doing it in steps of 0.3. So 0.3, 0.6, like that. And then now I plot xpaced and sine of xpaced. I specify what marker I want to use. Specifying the letter O indicates I want a circle as a marker. Okay, and O actually indicates a filled circle. And I say that the color should be red. Okay, so this is the color of the markers. The marker should be red in color, and the line style should be none. Okay. Now this is a mistake actually. This is a typo. Okay. If I actually said line style equal to none, maybe this is not a typo. Still it drew a line. Why is that? Okay, if you had given it the value line sign equal to none without the quotes, then it would not have. By default it draws a line. Okay, and since we didn't change, we changed the color of the markers to red, but we didn't change the color of the line. Therefore the line still comes out in which color? Blue, the default color. Okay. Now look at this. Plot xpaced np.cos xpaced. Now we are plotting the cos curve here. Okay. And b plus. Something has gone wrong here. I have to investigate. We'll run it afterwards if we have the time. We'll just run it. Because here the line style seems to have been set to none. And here you don't see actually the line. But you do see the markers. And the shape of the marker? B plus. Shorthand, a shortcut in order to specify both the color that you want to use and the marker that you want to use in one go. So I've told it B. B is short form for blue. So it puts blue colored square markers. That's what B plus indicates. Okay? And it didn't draw a line. I would have expected it to draw a line. We'll just change a few things later on towards the end in styles. Okay. Now, yeah, so I was wrong about this line style equal to none. Here again it says line style equal to none, and then it doesn't draw. Okay. So now we are again plotting sine, but now what we have done is we have separated, instead of using that shortcut B plus kind of thing, we have separated it to marker and color. Yeah. No, when I did B plus it didn't draw the line. Okay, maybe by default if you do that, then it says line style equal to none. Yeah, maybe we'll have to test that. Okay. But I don't understand then why it drew the line here. Why did this line get drawn? Interesting. Okay, we'll have to see. Line sign equal to none, it didn't draw a line. And it put those markers, again the same kind of O indicates you want circles and filled circles, and color indicates red. We don't have time to go into many of the other attributes, but you can control the size of the marker, for example. Okay, and in colors you are not restricted to named colors. You can give RGB color as well. I have an example of that later on. Okay, but there are many other attributes which you can specify, whether each marker should have a border, whether that border should be of a particular color, what should be the width of that border, etc. Yes. So mixing colors, I have an example of mixing colors. Okay. Yeah. And this of course was so exactly equivalent to this is this one. Okay. So yeah. So by default, I think if you give the shortcut, it doesn't draw the lines. It only draws the points. That seems to be correct. See, here we've specified line style equal to none, and it didn't draw a line. And we specified marker and color separately. And here we have given the same thing in one shot. Okay, RO, which means color should be R, and symbol should be a circle. And line style has not been set to none, but I think it assumes it in this shortcut, and it basically draws this. Okay. Okay. Now some more attributes. Okay. You can set line styles. Suppose you want dotted lines, dash dotted lines, etc. Okay. So what I've done here now, for the sine curve, I've said it should be red, and there should be circles which have been put over here. And I said line style equal to dash. Dash indicates a solid line. Okay. This is the default one anyway. But what I've done is I have set LW equal to 3.5. So width of the line is 1 in some units. What I've done now is I've said line width should be 3.5, which means 3.5 is thicker than normal. So you can see that this red line is now quite thick. For the cos curve, I have specified GS. What does that mean? Green squares. Okay. So the symbols are going to be green squares, as you can see here. And what is the line style? Dash dash. Dashed line actually. Okay. Instead of a solid line, the green thing has been drawn as a dashed line. Okay. So here's a quick summary of the line styles. Dash means solid line. Dash means dashed line. And dash dot means a dashed and dotted line, and colon indicates dotted line. Okay, so if you want a dotted line, there the symbol over here, line style, should be within single quotes colon. There are many symbols that are available. Okay, point marker, pixel marker, circle marker, triangle pointing down, triangle pointing up, and then there's a different kind of triangle. If you just put 1, 2, 3, 4 numbers there, then there's a square marker, there's a pentagon, there is a star, a hexagon, a different kind of size of hexagon, plus, cross, diamond, thin diamond, okay, vertical line, horizontal line, and so on. Okay. So these are the markers that are available, and as I said, every marker being an object has many attributes which you can manipulate, like its color, its size, and so on. Colors are available, and they can be specified in the following formats. So there are shortcut color names for the most frequently used colors, which include blue, green, red, cyan, magenta, yellow, black, and white. Okay, and there is a one-letter code for each of them. Okay, you'll get very quickly used to the code. So since blue and blacks both start with B, B refers to blue and K refers to black. Then there are RGB codes also. So if instead of in the single quote you put a hash and then you give a hexadecimal code, okay, I mean this is 256, so you have 2 bits to specify 2 hex bits for the R, G and B component. Okay, so what would this correspond to? FF0000. What's the value of R? What does FF correspond to in decimal? $15? No, F is 15. Okay, but FF is 255. Okay, so it corresponds to a very high intensity in red and 0 intensity in green and blue. So what color would that be? Red. So this corresponds to red color. Okay. You can also specify a tuple which has 4 values. These are the RGB values, and this is something called the transparency. Okay, a transparency of 1, I think, actually indicates that it's not transparent at all, but we have to check that. Okay, so it either indicates it's fully transparent or it's fully opaque. So I have one example where I show what is meant by alpha transparent. Okay. Then legends. Okay, you often have plots in which you need to mark legends. Okay. But before we get to legends, first we make the plot and we make a label. Okay. So you plot x, y and you label that curve with a string. Okay. Label equal to some string. Now this one is not labeled. Okay. Then I add a scatter. How do I add a scatter? I take the value of y that I have, okay, which is just that sin x, y is of course sin of x, and I add a random fluctuation about that value, which is drawn from a normal or a Gaussian distribution with a mean of 0, a standard deviation of 0.1, and length equal to the number of values in x. Okay, so it draws for every y, it draws from a normal distribution, okay, and it calls it y scatter. Yeah. So now I plot x comma y scatter. Okay. So these two have produced this curve. It's produced this blue curve and the green curve. This last line, what does it do? It plots those points, those fake data that we have, those little dots over there. Okay. And I say marker is equal to comma, and I put a label fake data with scatter. Okay. Now here, I think it only comes up there in the next one. What does the thing to remember is np.random.normal generated len x data points with mean 0 and sigma 0.1. Okay. So then what? So now here you don't have a legend, but to the same curve, okay, if you say legend, okay, and in brackets, then everything that has been labeled in the plot will have a legend box associated with it, and that box will be automatically put. Okay. If you actually wanted to change the positioning of the legend, if instead of putting, by default it puts it at top right corner, but suppose for some reason you want to put it here or here, okay, then you could do that. How would you do that? You would say that L equal to legend. Then that L become the legend object. Once you have the legend object, then you can change any of its attributes like its position, its size, the font that is used for the legend, okay, what is the color of the box that surrounds it, whether you want a box or don't want a box, etc. Okay, all that can be controlled once you gain access to that legend object. In this case, since we haven't put something equal to legend, and now the legend just come up with all its default values. Yeah. Correct. You will have to. There is only way of. No. Label is just a string. It's just an identifier of what the object is. So you can't really specify other than the text that you want there. Okay. You could specify, for example, raw text. If you wanted to put sin x, sin theta as the label, you could use a raw text here, okay, but that only specifies the text. You cannot control there what are the other attributes, like what font you want, what size you want, etc. That is only decided once you have the legend object. So that's an attribute of the legend object. Okay. Note that here we have not given a label to the cosine curve. and therefore that has not appeared in the legend. So only objects for which you give an explicit legend label will appear in the legend. Okay? This is the automatic way of doing things. Suppose for some reason there are also ways, which I won't go into, in which you can create a box by hand and then write whatever text you want and put whatever symbol you want. This is just a way of simplifying your life so that it's all automatic. You don't make any errors. You don't have to do it by hand. Okay? So both this thing, fake data with scatter, has appeared here, and sign of x has appeared here because they were put as labels to the curve. Okay. Now error bars. That's also very common. So what we do is we create a y error which is a random normal distribution between 0 and 0.2 and length of x spaced. Similarly, we create an x error which is np.repeat 0.1 len x spaced. What does np.repeat do? It just repeats the whatever value you give after that as the first argument, and the number of times it will repeat has to be specified in the second argument. So it will create an array which will be 0.1, 0.1, 0.1, 0.1 identical values. So for this example, we have chosen different random error bars along the y direction, but a fixed error bar along the of 0.1 along the x direction. Okay, and then we plot error bar equal to x spaced np sign dot x spaced, y error, x error, marker, color, e color gives you the color of the error bar. Okay, and marker is a square. So now notice here that it's in square marker and the default color is blue. It has drawn the markers in blue. It has drawn the sine curve in blue, but it has drawn the error bars in red because I have specified what is the error bar color, and I said I want it in red. Right? So you can control at that. Okay, you can control individual that particular, then change it. Okay, so explicitly you will have to do it one by one. It can be done, but it's tedious. But otherwise, you can give a separate error, of course, in both x and y direction, and you can control the error attributes. You can control, for example, what is the width of this red line, which specifies the error bar, and so on. Okay. Notice here that this error bar command actually plotted the curve along with the error bar. So it's not, there isn't a separate command to plot only the error bars. Okay. You could specify line style equal to none here, then it won't draw the curve, it will only put the points and show you the error bars. But the putting of the points and the showing of the error bars is all done with this single error bar command. Okay. Now remember, this object is now much more complicated. This error bar object is what is called a container object of three artists. Okay. So three artists are not artists, but it's three artist objects which have rendered it. So let's not go into that direction because it's basically class instances of the artists which have been created in order to render this plot. Okay. Now look at this. Now we are trying to take a real astronomical example, which is a curve of some object. So you have the modified Julian date listed on top as an array. Okay. Notice here that continuing on the next line is okay. Okay. Just put an enter and keep continuing. Okay. There's nothing special you need to do. You could have put everything on the same line as well. That also is not a problem. But just for readability, I just put an enter sign and it goes on. Then I give a magnitude of that at each of those Julian dates in the magnitudes. I give an error in those magnitudes which are specified by magnitude error. Okay. Which are specified here in this third line. And then I do the plot. Okay. Now, since I notice here that I have not specified the x error, okay, I have only specified the y error. Okay, and therefore I get y error is equal to, I specify the mag error, so error bars are only plotted along the y-axis. MJD is plotted along the x-axis and the magnitude is plotted along the y-axis. And here, as I said, I have given a RGB tuple as the color. So I can change those numbers and I can get absolutely any color that I want by changing these values. And I wanted the line width to be a little thick, so I said line width equal to 3. Notice here in this plot that Matplotlib has automatically subtracted a constant and made the plot more readable. Okay, so by default it tries to do some intelligent things, and of course in order to, you can change this, I mean you can force it not to do this, but what it has done is it's basically put an additive constant over here and made these numbers go from 0 to 0.35 for example. Okay, and it has plotted the magnitudes. Now normally the magnitude, if it's here, you want it, this thing to be reversed. That's not happening. Okay. Okay. Now this is an example of something that doesn't work. Okay. Remember, Kaustubh would have told you this, in any function when you give arguments, okay, you cannot give an unnamed keyword after a named keyword. Okay, you can give things in the default order, but no unnamed keyword after a named keyword. So what has gone wrong here is this arrow has been put. If this had been here before, this would have worked, but this doesn't work because you have given a named keyword, okay, something equal to something, before the unnamed one. Okay, but let's correct that mistake. Okay, so these are now the unnamed keywords. Once you start named keywords, everything else has to be named, something equal to something, that format. Okay, so what are we doing now here? We have given MJD and magnitude as before. We have given the y error. We have specified the markers to be circles. We have specified the colors of the markers to be red. We have specified the color of the error bar to be green, and we have specified the line style to be none. Okay, so no line is drawn connecting the 2 points, but all the data points with their respective errors has been plotted. Okay. So how do we now change this ordering? We want the fainter, this axis to be reversed so that the fainter objects are below and the brighter objects are higher up. Okay. Okay, so now we have in this code, we are going to flip the y-axis and remove the. How do we do that? This first thing is very similar to the previous one, but again we have changed some color here of the markers. But we have set ymin and ymax as the limits. I mean, we've taken the limits of the plot in the y direction and set it to two variables, ymin and ymax. Replotted the plot, plot.ylim, ymax comma ymin, instead of ymin comma ymax. We just swapped the order. Okay. Of course, all the points will then reverse automatically. Plot.tick label format, use offset equal to false. So that automatic offset in Julian date, modified Julian date, has now been removed, and all those numbers are now plotted next to each other. Okay. So the offset is not sub anymore, but things are looking very cluttered here. They're quite hard to read. So what one might want to do is one might want to rotate the text of the these numbers so that it becomes more readable. Okay, and that is what we do next. We rotate the X labels so that they become more readable. Again, this plot itself is done in a similar way. Again, we reverse the axis as before. We prevent it from doing an automatic offset, and we add one command which is called xticks, and we give it an attribute rotation is equal to 45. So the things get rotated by 45 degrees. Right? You can see the rotated values over here. It's also possible to make scatter plots. Okay, so in plotting curves, but suppose you just have a distribution of values and you want to make a scatter plot. Okay, so here I've taken a normal distribution. There are two identical normal distributions, but of course there are two instances. So you call the same function twice, you don't get the same set of random numbers. Okay, so you get some different set of random numbers, and then I say scatter distribution 1 comma distribution 2, x comma y kind of thing. Color is red. Marker I've given it, asked it to do a triangular marker, and I've said alpha is equal to 0.8. Set alpha equal to 1. Now I recollect, it will become solid. If I've said alpha is equal to 0.5, it will become more translucent. 0.3 will become even more translucent. And make it to 0, the point itself will disappear. Okay, but even if you make 0.01 or 0.02, it will be very, very faint, but still visible. This, of course, is useful when you are plotting many, many points together, and there is a danger that one point will fall on top of another point. Okay, by changing the transparency, you can ensure that the point which is hidden behind the point you have plotted afterwards, that point is also visible. Okay, so you should, anything that you plot after, the layers that you plot after the first set of points should be plotted with some transparency. Okay, histogram plots are also easy to do. Okay, so again I construct a normal distribution, this time with 100,000 points and a standard deviation of 1, and then I give a command called pylab.hist. Okay, I could easily have said hist, that's also okay. Distribution 1, the number of bins that I want to bin this distribution into, the color of the plot of the curve. Normed equal to true indicates that I want the histogram to be normalized. Okay, normalized meaning the area under the histogram should be equal to 1. The histogram type I specify as a step. Okay, otherwise the default make it look like a bar chart. Okay, but the step doesn't draw those vertical downward lines, and it shows me the histogram. Of course, since this is a Gaussian normal distribution, the histogram should look like a Gaussian, which it does once you have 100,000 points. This is simply one rendering of a Gaussian with a mean of 0 and a standard of 1. Okay. The last line is interesting because here I am just giving a single command, save fig, and giving it a file name, and will simply save that image. Whatever you see on the screen will get saved into a file. It's trivial to specify which format you want it in. .png in the PNG format, .jpg puts it in JPEG format, .eps puts it in encapsulated PostScript format, etc. .pdf puts it into a PDF format, and so on. So you can make your plot interactively, make sure it looks perfect, and then just add one line, save fig, give it a file name, done. Okay. Okay. So now, how do you do subplots? So in one figure you want to have, and you want to make a subplot. So first we define some curve. Okay, this is basically a cos curve and multiplied by an e raised to minus x kind of curve. Okay. And then we create, using a range, we can create two sets of numbers, one which are sort of spaced at 0.1, one which are spaced at 0.02, and then we basically plot, we do something called plt.subplot, 2 to 1. What does that indicate? It indicates you want a 2 by 2 plot, and now you are making the subplot for the first one. Okay, and I think it goes 1, 2, 3, 4. So in this case, 1, 2, 3, 4. Okay, and you notice here that for these 4 plots, only the last digit is changing. 1, 2, 3, 4. So 1, 2, 3, 4. Okay, so I've just plotted here various things. Okay, here you can directly specify this. You're making a function call in order to plot that function. Here you are simply plotting the cos function. Here you are now plotting the sine function. Here you are plotting some xy equal to x square kind of function. Okay, and colors are being changed, line styles are being changed, etc., etc. And we have now got our complicated plot with 4 different panels. And you can do this any number of times. I mean, if you want a 8 by 3 kind of panel, you'll say 8, 3, 1, and then 8, 3, 2, 8, 3, 24 would be your last one. Okay, so you can put data into any panel. You can repeat. Suppose you made all this thing, and then to the first plot you wanted to add a title. Okay, you would simply say plt.subplot 2 to 1, and then plt.title, give it a title string, you go and put it there. Okay. The last line is just to illustrate that with separate savefig commands, I've saved it as a PNG, I've saved it as a EPS, and I've saved it as a SVG. This is called scalable vector graphic. Very nice format for any kind of vector graphic. So that's it. So it's very easy to save. Now how about contour plots? Okay, here is one example of contour plots wherein I've again defined some function. Don't worry too much about this. Okay, and for n equal to 256, I basically create, instead of a range, I am now using linspace, and I create an x and y grid. This mesh grid, okay, I want you to go and look up what exactly this does. It basically creates a mesh grid which can be then used for making contours or any other plots. This axis command tells me what fraction of the total figure should be occupied by my plot. Okay, so this figure is a sort of bigger box than this. 0.025 to 0.95, 0.025 to 0.95 means about 5% of this edge has been left out. 2.5% of this edge has been sort of cut off. Okay, and then I give a command which does the contouring. There are 2 contour commands. One is simply called contour, but there is a nicer one called contour F, which does a filled contour. Okay, filled contour x, y. This is the z function which you want to contour over. This gives the number of levels that you want. This gives the alpha transparency of the filled histogram, and this gives you the color map that you want to use to map from levels to colors. So I've used something called cm.hot, but there are many different color maps that are available. You can also make your own color map, which is basically just a mapping from relative intensity to color. Okay. This generates those filled contours, but you actually also want to draw the contour lines, presumably. So this generated the contour F, generated these colored blocks. Okay. The next command, C equal to contour, okay, generated the actual contours, the lines, the curves, which are in black color. Okay, all of them. And then, since I had taken C as an object, I can change any of its attributes. I say C label C inline equal to 1 and font size equal to 20. Okay, so I have basically labeled all the values. So these numbers that you see 0.5, 0.25, etc. okay, have been labeled by this C label command with some default values. Notice that it has not necessarily tried to label every contour there. Okay, for example, the brightest contour which is here, that value is not specified, but these values are specified. Font size equal to 20 gives the size of this thing in points. If I made it font size equal to 10, then this 0.500 will shrink in size. Okay. Right. You can make lots of 3D plots with Matplotlib. Here is a small example of a standard Mexican hat kind of example. Okay. This is crucial. You may make a figure. Okay, now we have made the figure as a object. For that figure object, we say add subplot 111. 111 means it's going to be, the subplot is just going to be 1 by 1 by 1. Okay, but it's special in the sense that the projection to be used is 3D. So it tells it that this is going to be a 3D plot, whatever I am plotting. Then what we do is we create in polar space, we create the R and P data points, and then we mesh grid them onto some other variables R and P, and then we simply use the standard polar conversion to get x and y's, okay, as cos of x and r cos or theta, r sin theta kind of conversion. And then we define a function on top of those r's, okay, which is the z function. So now we are ready to, we have got x, y and z. Yeah. I have to check that, okay. I have to check that whether one can directly give this attribute, for example, plt.figure projection equal to 3D. Okay, that may be possible. I think that is possible. So you don't have to make a subplot, because since it's not really a subplot, one by one panel is not a subplot. Okay, so I think that should be possible. Okay, now the last command is what actually generates this surface for you. Okay, it's helpfully called plot surface. You have to give the x, y and z array that you want to plot. R stride and C stride, I don't know what that means. I think that probably refers to the viewing angle, okay, whether direction you are looking from. But I have to check that, what that means. And then I have now used, instead of hot, I have used a different color map, which is called cool, which is instead of different shades of red and orange, different shades of blue. And I have actually shaded the plot. Okay. Now see what this thing is. This object is part of what is called a poly 3D collection. Okay. And it's located at this memory address. Okay. So this is with 3D plots. Okay. So far we've done what was a very, very quick tour of the capabilities of Matplotlib. But we have looked at many things. We have looked at how XY plots are made, okay, how to change labels, how to label the axes, how to change the fonts, how to make things italics, how to make things bold, how to control which markers to use, how to control the colors of those markers, how to draw lines and not draw lines, or draw lines with different line styles, dotted lines and dashed lines and so on. Then we have looked at various other kinds of plots, okay, 3D plots, for example, contour plots and things like that. So I looked at how error bars are plotted and how to control the plotting of error bars, etc. But this time is inadequate to actually go into things in great detail. If one wants to go in great detail, then this is the thing to remember. Okay, go through the example. There are 1,000 examples, okay, for you to look at. Okay, this is the URL, matplotlib.org, gallery.html. Sometimes what I found useful is that I just go look through the gallery and the closest to the kind of plot I want to make, then look at the source code, even take that source code and just modify it for my requirement. So you can try that same strategy. And of course, making plots takes a lot of time and effort, but Matplotlib, so this doesn't save you from that time and effort. So if you want to make a publication quality plot where everything has to be exactly right, okay, then you will have to play around. You that capability, but it also requires you to spend time. I mean, if you know any of the commands and what they mean and what are the exact attributes associated with the command and so on, and what they mean. So that you will have to do anyway. But for quick and dirty plots, wherein you just want to just plot something against something else, is quite easy. What I have not covered today is a module, separate module called APLPy. It's called ApplePy by some people. It's the astronomical plotting library in Python. And basically what it is, it's a Python module that sits on top of Matplotlib and adds some more functionality that Matplotlib doesn't have. This functionality is mostly in the area of showing images. Suppose you have images and you then on top want to plot right ascension, declination, grade, or want to put insets of one image and another image on top, etc., etc. So that capability APLPy provides with the use of very simple functions. So if you need to show some astronomical data and need a system that very well understands world coordinate systems and plots them correctly and so on, then you should definitely look at APLPy. APLPy also has some modules by which you can very, very simply download data from some archives and create images, even color images. So for example, with APLPy, you can an array deck and get data from JPGs and just make a image of that. So it's like literally to do this. Specify your array deck to make a color image. It will fetch all the images over the net. It will scale them, it will align them, it will combine them and show you the colored JPG or something like that. Okay. Yeah. So this is, I think, it as far as thing is concerned. Next time we will have Kaustubh speaking to you on Friday, and he's going to cover some leftover topics in Python, miscellaneous topics in Python. And then next week we will have only 2 lectures. The last 2 lectures of this course. One will be focused on how to use Fortran and C codes from within Python, and the second one will be focused on AstroPy, which is this astronomical Python module. So are there any questions? Yeah. Yes. 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 Correct. So it depends, the answer solely depends on whether you expect to do extensive modifications to the subplot that you are making. Okay. If what you need is routine, okay, but often it is not. See, for a first cut, you are better off using the PL commands. Okay, but if you actually want later on when you do publication quality, then you'll see that okay, these numbers or this line is not exactly aligned with that line of that subplot, and you want to move it slightly to the left, or the legend has come too much in the corner, you want to move it slightly down, etc. The moment you reach that situation, then you need handle on the object. But I mean, it's just a trivial question. It's very, very easy to switch from one to the other. You may have to change 4 or 5 lines of code, and then you are switched. So, I mean, the quickest way, if you are doing test plots, I would say do it with PyLab. And if you are actually doing final publication plots, then you do it with PLT, because you will need to do that. PyPlot is, it does these defaults are not always the best. So you will have to make changes. Yeah. Any other? So this, I would like to emphasize that the notebook of this is going to be very important for you to play around with. Okay? Because it's great fun to change the line weight, change the color, change this, change the symbols. Because that will really teach you very quickly how things work. Okay? Yeah. So please, once we upload the talk, it will hopefully come up. Yeah, it should come up by 5 or 6 p.m. today. At least one notebook and use it. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. At least about half of you, but the other half have not. So please do it. Without that, this thing will not be sustained. Remember, we did this course in February this year at Ayuka, and we did whatever we are teaching you over 3 weeks was taught over 3 days. People had simply no time to absorb new things. You have a very good advantage that there are 2 days gap between successive lectures. There is time for you to go back and practice whatever you have learned. Okay? If you practice, it won't be retained. These things, none of these things are very complicated or difficult to understand. It's very simple. Python is a very simple language, but it still requires practice. Okay. So I'll stop here.